The outline of the talk is like this. I will try to explain what did lead to this recent success of recurrent networks and deep networks that we did observe in the last 2 years from my perspective. And I will try to explain what is the concept of longer short-term memory, because I think this is something that many people ask me about, the concepts of the exploding, vanishing gradients. What does it mean, and how can we make recurrent networks that can remember more of the things, how to form better types of memory. So I will try to first explain the longer type of the short-term memory, and then I will try to talk more about the long-term memory. So I will try to identify the limitations of the recurrent networks and describe our ongoing work, how we are trying to overcome these limitations and learn the long-term memory and recurrent networks, basically, or maybe something beyond that will be able to, some machine learning technique that will be able to learn much more than what we can learn with the current techniques. And at the end, I will be discussing how we can possibly build intelligent machines that would understand language, because that was my primary motivation when I started my PhD. I wanted to have machines that can really understand the language the same way as people do and communicate with us, and basically improve this interaction with the machine so that it would become much more natural. So instead of programming the machines, we would be just able to tell them what to do. And I think this is the distant future, but it's how computers will evolve, in my opinion. So for the history of the recurrent networks, it's good to realize that actually much of the work that is influencing the current techniques has been already done by many famous researchers already, in the 80s and early 90s, those that did work on recurrent networks. Some of them are listed here, like Jeff Ellman, Mike Jordan, Mike Moser, and so on. There was tens of researchers who did do very influential and important work, and as I will be showing later, many of the ideas that are reoccurring these days are actually combinations of the previous ideas. The reason why people were so much interested in the recurrent nets was that the idea seems to be very attractive, to have a model that can form this kind of memory by reusing the parameters and computation over time. So this is the maybe most famous architecture of recurrent network. It's coming from Jeff Ellman. It's often called Ellman network, and it has been presented in his paper, Finding Structure in Time. There are some very basic components that probably most of the people did already see before. There's input layer and the hidden layer and the output layer, and the hidden layer is connected to itself through the recurrent connections, so that it has a chance to form short-term memory, because that is represented by the state of the hidden layer. So this is a graphical representation. The training of this model is about modifying the weight matrices between these layers, which are denoted here as U, V, and W. Well, as I said, there was many researchers who did work on these techniques, but somehow they did vanish from the mainstream research after the initial excitement. And even if people did know that these models can be very powerful in theory, they were considered to be unstable to be trained with the standard optimization techniques like stochastic gradient descent, and people were struggling to make them work for a long time. It also should be said that actually there was a group at Technical University of Munich around Jürgen Schmidhuber, who later moved to ETSIA and did work most of his career on the so-called long short-term memory recurrent network architecture. So this one actually did work, but the model was too complicated for others to reproduce easily. I did actually speak with speech recognition researchers at 2009, 2010 about why they didn't consider these networks ever to be used, for example, for acoustic modeling, and really the reason was that people were afraid of the complexity of the architecture back then. In 2010, I think that there was kind of a small breakthrough in the language modeling community, And that was when I was able to show that recurrent networks can actually significantly improve state-of-the-art in language modeling, machine translation, data compression, and speech recognition. All these problems basically can be solved better by using the RNLMs. And I did publish the code, which I think helped a lot of people to get convinced that the results are good because they could reproduce them themselves. And later, when I was trying to figure out with other researchers, like what was the reason that the training did work for me while it was not working for others, was that I did come up with this trick to clip the gradients to prevent the instability, which did turn out to be quite crucial, which I didn't realize back then. I did just think that I have a bug in my code and I have to solve it by clipping the gradients, but it did turn out to be like more important. So just to show some results from these years, I have all of this in my PhD thesis. This is the setup obtained with a simple version of the Kaldi speech recognizer, and here the unbased scoring was giving like huge reduction of the word rate. So many people actually did start paying attention to these models after seeing these results, because they're like the best Ngram model can be beaten by like more than 20% in word rate by this combination of big recurrent network language models. In this case, they were also trained with some Ngram features, which is described in my papers. But the main point is that like a big reduction of word rate suddenly became possible, which is something that the language modeling community was kind of slightly struggling to achieve for like many years. And this improvement was significant enough for many people to start paying attention. Then another result that I think was did get many people actually excited even more about these models was that I did show that that with more data, the improvement that the recurrent networks achieve over Ngrams, the improvement is actually increasing. So this is quite unlike many of the previous language modeling techniques, like the class-based language models. They actually, the improvement is actually vanishing. The more data we use, the smaller improvement we get, and that was the reason why many people in companies were not interested in language modeling research, because they did think that if they scale the models to very large data sets, that there will be no difference. But it was different with the recurrent networks, because this graph already shows that the improvement is getting bigger and bigger. So it's really a very useful technique to use for very large data sets if we can train these networks, because they are, of course, computationally complex. And then one other result from my PhD thesis, which is kind of more like fun result, because I didn't really see many people working on data compression with recurrent network, but basically we can just combine RNN and LM at arithmetic coding to it, and we obtain like a great data compressor, which is like more than twice better than gzip for compressing text files, and slightly better than the state-of-the-art compressor that I could find, which was the PAQ compressor from Matt Mahoney. Then another result that was like very influential was was obtained on the IBM setup, the NIST RT04. The improvement in the word array that we obtained with Anup Deras from Johns Hopkins University was more like 11% reduction of the word rate, and this setup was pretty big. There was like 400 million words for training the language model. The vocabulary was like 80,000 words, so that we had to train models that were like orders of magnitude larger than the previously trained biggest neural net language models. And from the graphs here, it's obvious that the bigger model we train, because there is shown the hidden layer size and the word rate in this figure, the bigger models we can train, the bigger improvement we obtain. So that was really like exciting result, because even the graph didn't stop for us, and if we could train a bigger model, it was obvious that we could get even bigger improvements. So it's like 2012, and then of course recurrent networks became very popular because they were implemented in general machine learning toolkits like Theano, Torch, PyBrain, TensorFlow recently, and quite a few others. So there was like the exciting things. I think that today it's already like well known that the recurrent networks are like applied in many of the systems that are used in competitions in academia, even in systems that are used in industry to do both like acoustic and language modeling in speech recognition, in machine translation community. People use them basically to do everything. So there are even like architectures that do MT just based on the recurrent networks and nothing else. And then there are like many NLP applications, like the list would be very long and so on. I think that the downside now is becoming that people just are starting to believe that solution to everything is just some sort of some kind of recurrent network, and often they just use them even in places where a simpler model would work well. So I think it's good actually to not just use the recurrent networks, but also understand what they actually are doing. So this is going to be one of the goals of this talk, to explain that that these models have some limitations as well. So at Facebook, we did publish like in 2014 and presented in 2015 at iClear workshop this paper called Learning Longer Memory in Recurrent Neural Networks that actually explains like, or it shows a simple trick how to learn a recurrent network with some kind of longer short-term memory without any unnecessary complexity. So if we would go back to the Elman architecture, there is just this simple figure that shows that there are these weight matrices, like going from input layer X to hidden layer H, and then to output layer where is the probability distribution over the next word, that's Y, and then there are the weight matrices A, R, and U. So this is already what we have seen before, just with different letters. Here are the equations that correspond to this model. There are sigmoid activation function in the hidden layer, and softmax in the output layer. So the model can be actually described with just few equations. It's pretty simple. As I said, like it was well known that there are these problems that the gradients during training, if we use stochastic gradient and descent, and as we propagate the gradients back through the structure back in time, then the gradients, their magnitude, like almost always is decreasing. This is called a vanishing gradient problem. That means that the network will not pay attention to what happened a long time in the past, so that it will not form this longer short-term memory, just a short-term memory. Or sometimes the gradients can explode, which does lead to instability in the training that can be somewhat solved with the gradient clipping that I already mentioned. So even if it's kind of a hack, it was like important to make the networks stable. So for the vanishing gradient, the solution is a bit more tricky, and as I said, the gradients usually vanish quite quickly, decrease in magnitude, get close to zero, and the network just focuses on the last few words in language modeling. It just doesn't get much back in time. The state of the hidden layer basically represents just the last, say, 5-10 words of the history. And many people that believe that this is the problem of SGD, that we have to come with some more like fancy training algorithms, like second order optimization and so on. But on the other hand, we actually look at the recurrent networks, what was actually successful in the past. It was often like some structural modification of the recurrent network. It was some different architecture. So this is what we explore in this paper, and so we were like thinking what can I learn longer term patterns, and there is this inspiration from the papers coming from 80s, and there were networks that were invented, I think, by Mike Jordan and used quite extensively by Mike Moser, where the weight matrix for the recurrent connections is not full, but it's just diagonal. So each neuron is not connected, each neuron in the hidden layer, in the recurrent hidden layer, is not connected to each neuron in the next time step of the hidden layer, but it's connected just to itself. So that's like what it means to have a diagonal recurrent layer. So of course the Moser network would give us a worse result than the Elman network, but the simple idea is to basically connect both these ideas together in a single architecture. There are like several explanations that we discuss in the paper. I think one of the attractive ones is to see the model as having two hidden layers, one that is fully connected and the other one denoted in this figure as ST, that is connected just with some diagonal weight matrix. That means that each neuron is just connected to itself. And for even making it simpler, we did just choose to keep this weight fixed to show that really this model learns the longer term memory by having small changes of the state layer that represents the longer short-term memory. So as I said, the alpha value, the weight that corresponds to how each neuron is connected to itself is close to 1, like 0.95 in our experiments that I will be describing later. That means that the state of the neuron in the state layer will be something like 0.95 of the previous value plus 0.05 of the contribution coming from the input layer that is learned. So this state layer will be changing very slowly, and that allows it to form the longer memory. And we did decide to name this architecture structurally constrained recurrent network because it can be seen as some constraint on the recurrent matrix. We can actually have a single hidden layer with recurrent connections, some of them being turned off. It can be seen as having hard zeros in the recurrent matrix, and we discussed this explicitly in the paper. Alternative name for this architecture can be slow recurrent network, because the main concept is that there is this part of the hidden layer that changes the state slowly. There was actually a paper that other researchers from Google Brain did publish like half a year after us that actually is trying to use the same trick. Just instead of having the constraint on the weight matrix, they just constrain it in the beginning. So they just initialize the recurrent network with diagonal matrix. So sometimes people ask me whether these ideas are the same. Actually, they are not. If we would just constrain the matrix to be diagonal in the beginning, but during training we would allow it to become again fully connected, then this would again not allow the recurrent network to form the longer memory. It would just again degrade into the normal recurrent network. So people can really try this easily out themselves, because training recurrent network with this diagonal initialization is very simple, and training our model is simple as well, because we did publish both the data sets that are used in the paper and the code, so it's available. And now the experiments, there was this hypothesis that actually these longer memories in recurrent networks correspond to like cache models, that they are very similar, and and that's why we did report experiments on two data sets. One of them is Pentry Bank. We did observe that there's like 10% perplexity reduction by using a cache model, which is like this language model over like a longer history, which is dynamically interpolated with the n-gram probabilities. And we did observe like very similar gains over simpler recurrent network with these longer short-term memory types of recurrent networks. Again, like it was around 10%, and actually LSTM and SCR did get pretty much the same performance. And we did do the same for a bigger data set, which is part of Wikipedia. The cache patterns are much stronger there, because Wikipedia articles have higher diversity than the Wall Street Journal articles that the Pentry Bank is made out of. And here the cache was helping much more in perplexity, like going from 309 to 229. So it was like bigger reduction, and we did observe also like bigger reduction from like these models that learn this longer memory. In this case, we did use just a small model, and actually LSTM is much bigger for the same number of hidden units. And still the SCR was actually quite a lot better. When we did increase the size of the hidden layer, then this improvement did vanish. So it seems that LSTM can learn like the same as SCR, maybe even a bit more parameters. But it seems that for comparably large models, we would get clearly a better performance with the SCR, because because LSTM has all these input gates, output gates, forget gates. I think that many people who know this architecture know how complicated it is. I will be not really showing the LSTM model here because explaining it would take a long time, but it's basically a complex architecture, and the SCR, as I said, is way simpler. So I think that we did like empirically prove that this longer short-term memory in language modeling basically means the same as what people used to call topic models or cache models, and it's a very simple idea. So I think that this way we want to also like explain that the recurrent networks do not really understand the language. They are like very nice models, but if you want to understand language, we actually have to do much more than just kind of like a back of words over last 100 words, which is actually what this model pretty much learns. And for infinitely large or very large training sets, the SCR net seems to be actually a preferable architecture because it doesn't have all these gating mechanisms. It has just this short diagonal layer that's very cheap to evaluate. So for the conclusion for this part of the talk, I would say that very simple tricks can in the end overcome the vanishing and exploring gradient problems somewhat. I wouldn't really solve it, but it's kind of works more or less. And if you want to actually learn like some kind of long-time memories, some type of memory that we as humans have when we, for example, can remember what happened 5 years ago, then this is not going to happen. At least it doesn't seem to be the case with recurrent networks that just recompute all the state of the hidden layer at every time step. This is not how we think of the long-term memory. So it seems that we have to develop some different architecture, which I will be talking slightly in the second part of the talk, but it is still like unsolved problem for us. And we believe that long-term memory is like an example of some type of growing architecture. So one can think of recurrent network that can learn when it needs to add neurons to itself, and for that I will be describing this architecture just in a while. So what can we do to do something better than recurrent networks, like how to go beyond deep learning and beyond recurrent networks? Well, it's interesting to see that actually there are like very simple patterns that these models cannot really learn efficiently. I was describing some of them in my PhD thesis, just like remembering, for example, a sequence of symbols is already like a pattern that cannot be learned, even if it has very short description length. These networks can memorize everything, but they can't really learn these concepts. They can't learn algorithms. So we call like these complex patterns algorithmic patterns because they really often have very short description length. And like for people with computer science background, like it will be obvious to know like these examples like AN, BN. That's basically a pattern that cannot be learned with Einstein machine, but can be learned with context-free grammars or sequence memorization that I was mentioning just before. Or what we did in a paper is learning, for example, to add numbers just from examples. Like all these patterns are like beyond what recurrent networks can learn from just unsupervised learning from sequences. So that's what we aim for, like in the future, to relearn these complex patterns that actually occur regularly in language. Maybe not the binary addition, but definitely patterns like being able to repeat a sentence that we did here. That's definitely something that we can do, but recurrent networks cannot do, and it's a very simple problem. So one can of course think like there's so many possible problems like that the recurrent networks will fail at. So what should we focus on? There are so many paths forward. So instead of like trying to go like one step forward at a time, we did change a little bit by saying that we will first set what is the end goal, what is the main thing that we want to do, and then we would define a roadmap how to get to this goal by like naming what kind of properties the models need to have to be able to actually get there. So the final goal for us is actually machine intelligence, which is like the second part of the talk that I will be describing. Just if I can check how much time do I have. 9:35. Okay, so still half an hour. Good. So just skip the slides. So this is the second part, and it's joint work with Armand and Marco, and we did publish this paper like several months ago, and there we actually first tried to like say what is like a reasonable goal for having a minimally complex machine that we can call intelligent, that can really do a lot of like useful things for us. And we did come up with this proposal that I will describe. We think that really the core of the intelligent machine should be some kind of like a machine that can communicate with us, that it can learn from us, and that can accomplish like any range of tasks for us. Not just the tasks that we would hard code, but a machine that would learn from the communication with us to do anything the same way as humans learn when they interact with each other. So the use cases can be like very diverse, like helping students to do homeworks by like teaching them, or helping researchers to like find relevant information and understand the information, maybe even like write papers for them. That would be great, right? And even for computer science, people like for programmers like to have a machine that really can write the programs or basically execute the simple instructions automatically, so that we would just say like what is the end goal, like what is the task, and the machine would be able to just produce the corresponding sequence of instructions. So this is what we aim for. This like the artificial intelligence for us, and we did try to come up with a minimal set of components that we think that the intelligent machine will need to have, which of course is something that different people can have different opinion on. So we don't want to claim that our roadmap is the only one. It's just the one that we find the most interesting for us. And then we discuss in the paper approach how to construct the machine and the requirements, how to make this machine to be really like scalable, so that they would be able to learn quickly new things. So the components that we did like come up with that we think cannot be reduced further are ability to communicate. Like if we would come up with artificial intelligence that cannot communicate with us by, for example, building a computer that can play, for example, StarCraft very well, that would be like a great achievement, because that's not doable today. But except being able to play this single game, how can we communicate with such intelligence? It's not clear at all. So if there's no way how to communicate with the intelligent machine, then it's not a useful intelligent machine. And we want to build the intelligent machines that are actually useful for people. And there has to be some motivation component. It's just not enough to basically talk with the machine, but we have to be able to specify like what it's doing right, what it's doing wrong in some natural way, so that we can really motivate it to do something for us. And so first it has to be able to understand us, and the second thing is just to pay attention to what we are saying. And then it needs to have learning skills, so some unbounded learning skills. It should be really able to learn like any task, and that will again require the long-term memory, which no machine learning technique that I know of actually has in a general form. So for the components of the framework, which is like the framework that we think that the intelligent machine can be like built in, it's kind of like a framework where it will like kind of grow as we see it. We think of some kind of simulated environment, because we can't think of like having the machine immediately connected to people who will teach it, because we don't know how to build a machine. We have to try like many different techniques and do a lot of research, and this has to be done automatically so that the experience would be reproducible. So we think that there can be a scripted, simulated environment that would be aiming to teach the machine some basic communication skills, where the humans will be replaced by subscripted entities, and there will be some communication channels and the rewards for the motivation component. And we believe that the core of human learning is that we can build or base our knowledge on what was learned by previous generations by other researchers. There's really like very much like incremental hierarchical structure of our own knowledge and intelligence, and we believe that this should be also part of the framework. Is the same as like if we build a school for children, also they will need to face simple problems first, then more complicated problems that are using the previous ones. Before you want to study, for example, computer science, it's good if you learn how to read and write, and so on and so on. So the framework for learning for teaching the intelligent machines should have this incremental structure. Then we need basically to develop this environment that doesn't exist yet, because we don't know about anything that will be like useful for this purpose. So we have to develop this data set that will be having the right complexity. If we would, for example, add the complexity too quickly, then basically the solution might not even exist. It's like asking a machine to like read newspaper articles and answer some questions about them today. I think it's completely impossible, and many people actually try to do this. And I think it's like just a too big jump, like leap from where we are to what we want to have. And there's basically no way how to have, for example, support vector machine to be able to answer complicated questions about some stories. And actually many people did try to do that, and then the results are kind of like not very good. So I think the complexity cannot be added to the simulated environment too quickly, because there's no way even for a human to succeed in such situation. It's like if somebody would give you like thousands of newspaper articles written in Czech and ask you about answering the questions, like there's no way a human would be able to succeed, because the way how we learn language, it's much more like interactive. We have to be able to learn first the simple concepts, and through some interaction with others we can refine our knowledge. And if you would be adding the complexity too slowly, that also happens sometimes, where people use a technique to learn some very, very simple, for example, artificial computer game by exploring just brute forcing the search space. That's also like missing the final goal, because if we add the complexity too slowly, maybe we will just be convinced that a technique that is in principle very trivial works for doing something where it actually doesn't do what we believe that's happening. So for the high-level description, we have like these components, like the learner, which stands for the intelligent machine that does all the learning. And there's a teacher that replaces the human in this environment and tries to teach the learner like the communication skills. And then there are the rewards that the teacher specifies for the learner for accomplishing tasks. And for scaling this up, like that's the crucial part. We need to add more complicated tasks at the right speed and provide less examples. And definitely we want to make the training as unsupervised as possible, because otherwise we would just fooling ourselves. If we tell exactly the machine what we should be doing at every task, then it would be kind of easy to succeed on the simple ones, but then such approach would never scale. So to be really scalable, we need to focus on learning quickly from few examples and with a very small amount of supervision. So these are like more like in detailed description of the agents in the simulated environment. Like the teacher and the environment are based on some simple scripts and the teacher provides the tasks, and everything is basically supposed to be scripted. And later we will replace the teacher by a human who will be like in this artificial environment, providing the goals for the learner that tries to maximize the average incoming reward, which I think is the key concept here, that the objective function is not to optimize accuracy on some held out data or on some test data, but the objective function is to learn as quickly as possible, so that we should prefer the machines that need to see less examples and that need to do less steps before they reach the goals. So if you would think, for example, about playing artificial games, the crucial difference here is that we don't really care about what is the final performance of the machine. We care about how long does it take for the machine before it gets to certain performance. So if you want to play, for example, Tetris or some other simple game, if you need to play like 100 billion simulations before you learn how to play the game, that's not really intelligent. We need to have a machine that will be able to learn from, like, say, 10 or 100 trials, and the objective function that we are optimizing should reflect this. That's what we should be aiming for. And further, as I said, like, everything in our environment is based on communication. So there are like these communication channels that teacher and environment can write to the learner's input channel, and the learner can, like, pretty much say what it wants to say in its output channel. And the rewards are also like parts of these communication channels. So here's like simple visualization. We are thinking of some 2D environment. It would look like some very, very simple game that's supposed to teach the machine here, like as this small robot, to understand some simple commands from the teacher. Like here are like the input and output channels shown as here, where the teacher says like some simple task like move and look, and once the robot can, like, remember this command and produce the correct sequence of instructions for the environment, then it achieves the reward. This is already in a situation where the learner knows what it is supposed to do, so it already learned this task. So how to scale up? As I said, like, the crucial part is to focus on, like, speed of the learning, like not the final performance, but how long does it take to get there, like how many training examples have to be seen before the machine gets to the performance. So we need to focus on generalization, not on memorization. Many of the recent deep learning results look good, but they are like examples of great memorization. They are not examples of great generalization. So here we really aim for generalization. And then, as I said, like, later we can certainly add humans, but this is still far away, because even the simple environment that I'm describing, like, we don't really have techniques that will be able to do well there, even if we are trying to do something. I will describe, like, in a while, a simple model that we are working on, but it's still far away from being able to solve this environment. And the real-world signals can be also added very easily to the simulated world, because we can have just part of the input-output channels can be like simple scripts that react to what the learner is saying by allowing it to form queries that will be sent to internet, and the result can be sent back to the input channel of the learner. So, as I said, we need to develop new techniques that will be able to do much more than the RNNs. Very, very simplified tasks can be like this type of like context-free grammars, and some very simple Turing-complete problems. We did show, like, recently last year in this paper, inferring algorithmic patterns with stack augmented recurrent networks, that we can actually learn something more than normal recurrent network if we augment the recurrent net with some kind of external memory that has some specific topology. As I said, like, we want to have machine learning techniques that can have these properties, like that we are listing here, like to be able to represent any computation, so like to be Turing complete, to be able to form the long-term memory, to be able to do incremental compositional learning, and learn quickly from small number of examples with very like in a very unsupervised way, with just small amount of supervision coming through rewards. So not the supervised learning as we normally use. And there are like these small steps forward. Again, like, it's based on old ideas that people are already exploring before. We were able to do something better than before. Still, as I said, more work needs to be done. So I will be describing now in the last part of the talk this paper about the stack RNNs. It's a very simple model. It's like a recurrent network that operates like decides what it will be doing with this external memory. We can see the most simple cases when we have a single stack, that the hidden layer basically of the network is kind of like controlling, because it produces values that influence the distribution over the actions in the action layer. And the actions are like the basic stack operations, like push a value, and even the value is of course computed by the hidden layer. as the D matrix, or pop a value or do no operations, like not move anything with the stack. And there are, of course, like many other like computer science structures of memory that are like very well known, like tapes and queues and 2D, 3D grids and so on. And of course, we can have multiple stacks, which we actually do in the model. So we have explanation of how this model can be seen as, again, like some structurally constrained recurrent network. That's more in the paper. It will take a while to describe it. So I think I will just skip the explanation, but it's really like very simple in the end, and it's quite related to the previous part of the talk where I was showing the diagonal matrix that basically allows the state of the neurons to stay the same, and that can be seen as no operation on the stacks, and the push and pop are basically off by one diagonal matrices. And everything is trained by SGD, and here are the examples of the patterns that we considered first. And these are known to be learnable even with LSTM, because LSTM has a chance to basically use a linear part of itself to do counting. So all these problems can be actually solved with counting. So there are like these sequences of symbols that are generated. Some of the symbols are deterministic. So if the model that is learning a language model and minimizing perplexity, if it learns correctly the algorithm behind this that is inside of these sequences, then it can generalize. So we did show that the stack RNNs can generalize pretty much as well as the LSTMs, plus minus some accuracy. That doesn't really matter that much, but both these models can count, RNN cannot count. But then we can go like to more complicated tasks where we are showing that we can actually even memorize sequences, which LSTM cannot do, because a model that can count can of course solve like these context-free patterns that are about counting. But if you want to remember variable length sequence of symbols and then reproduce it later, that's already where LSTM fails and the stack RNNs work. And even more like exciting was the binary addition, where we did teach the machine again like in a language modeling way just to predict the next symbol. And it was able to learn this complicated functionality when it had 10 stacks, that it did learn to add binary numbers by just observing the sequences in an unsupervised way. So it did learn to store the first number, store the second number on different stacks, and then recall this information from the stacks and combine it together to form the solution. So here, like the green color means that the particular stack is pushing the information. The number means what is on the top of the stack, and the red color means pop operation. So this is a figure that would take probably like 5 minutes to really explain well, but we have it in the paper. So I think it's quite interesting to know that like just SGD training did allow us to learn this kind of computation, this kind of automaton that does the computation. And it generalizes to large lengths that then it was trained on, which is like the core of the learning. So the good things about these stack RNNs is that it's a Turing complete computational model, so it can represent in fixed length any kind of computation, and it's able to grow its size adaptively to like any size. Like it can really grow to infinity. It learns some algorithmic patterns and has some sort of long-term memory, even if it's not really that type that we would like to achieve, and works on some problems that were before unsolvable with both RNNs and the LSTMs. And we also published the code. The bad things are like still unsolved problems are that this type of long-term memory doesn't really store the logic in the long-term memory. It stores just the partial computation. So it's just using the stacks to like store like the length of the sequence and stuff like that. But the algorithm about like this A and B, and it's still stored in the weight matrices, and we believe that still has to be improved because otherwise we can't really do incremental learning with this model. So that still doesn't work. And stacks, of course, are like the simplest choice, but it doesn't seem to be the best choice of the topology of the memory. So as a conclusion, I think that if we want to achieve artificial intelligence and really like language models that understand the language and computers that can talk with us, we need to set some ambitious AI complete goal, and we need to develop these new tasks, because currently we are even missing the tasks that would be good for measuring the progress. And we need to develop like new techniques, and everything has to be kind of done together. If we just fail on setting the right goal, then we can be completely work on the wrong thing. And then we have to motivate people to address these problems, because I think that we really need to build a community of researchers who really know what we are aiming for with these recurrent networks and deep learning and so on techniques. So okay, thanks for the attention, and if people have questions, then just ask me.
We have time for plenty of questions, so do anyone have any questions? Then I will ask the first question.
Okay.
And to let the machine keep the skill it learned, I mean, if you learn a machine which can do the multiplication, then you ask the model to train on the addition, probably it will forget what it already has learned. So to make the machine keep the skill it has learned, do you have any idea how machine can achieve that? Thank you very much.
Yeah, I think that's actually the crucial thing, that, as I said, we didn't solve it yet, and we know that we actually have to solve it if we want to achieve the intelligence. So we are thinking hard about this problem, and we have some ongoing work that maybe can do this. As I was saying, if we can learn the logic inside of some long-term memory structure, then that would be so much better than if we learn the logic in the neural network weights, because the neural network weights are overwritten. They change whenever we face a new problem. So you basically keep forgetting the old things. So if we can store the logic in some sort of long-term memory that will stay fixed, it's the same as, if, for example, if you learn how to ride a bike, and then you want to, for example, learn how to program in C++, you don't need to overwrite your neurons that are like related to like the skills that are related to riding the bike. You can just keep it somewhere frozen and not really lose this skill, and just create new skills in some other regions of your brain. So we as humans definitely do it, and it's like crucial for intelligence. And neural networks, recurrent networks, LSTMs or whatever, they just don't do it, and we really have to aim for this.
Thank you for your insight. Do anyone have other questions? Oh, there's a question.
Would creating an AI part of the AI complete goals?
Sorry, I didn't hear the first part.
So, for example, should an AI be able to create another AI?
AI create another AI. Well, that's like what people are thinking about, this technological singularity, that if you get to the point that you really build an intelligent machine, then if it's really intelligent, it should be also able to build another intelligent machine, and it should be kind of like able to, this way, self-improve itself. So this is like what some people are like talking about, especially in the science fiction, and or like people call it, I think, this technological singularity. I think that we are quite far away from that point. So in theory, I would say yes, but before we have AI that can build another smarter AI, then we have to build like this AI that can at least like memorize the sequence. So yeah.
Do anyone have questions? And I have the third question. My question is for the stack RNN. Stack is probably just a very simple function. So for your next step toward the machine intelligence, what is the next functionality you think we should add to the stack RNN? For example, probably random access or other functionality you think we should add to the model? Thank you.
Actually, that's also like what many people were thinking of. Like after we did publish this paper, like a half year after that, or I think it was last December, that people in the Google Brain team did actually consider like very similar model to ours, but with the random access memory. So that's also like been already somewhat explored. It's not completely clear what is the best type of the memory. As I was saying, the stacks have some. So they are not very natural in some sense. For example, like all these memorization tasks that we do, we were like doing them as a proof of concept. So we can memorize a sequence and learn a logic that will able to to reproduce the sequence in reverse order, but not in the original order, because if you know like how the stacks work, it would be very clumsy. You would need two stacks, you would have to copy things here and there. It's actually much harder, even if you would want to manually write a Turing machine that can do it, or a Feinstein machine controller over two tapes, or over two stacks. So we think that actually much more natural and much like a human-like type of memory would be probably not stacks, which are the simplest type of serial memory, but we are thinking of parallel types of memory, and we have like some ongoing work already going for like a half a year, and there are like some working ideas already. We shall see how far it goes, but definitely we have like different types of memory that can actually work better than the stacks, even on like these problems that we as humans consider natural. So I think that parallel computation models are still very interesting. If you know, for example, the cellular automatons that can kind of like grow in complexity, that's like very exciting property, and we are exploring it now.
Thank you very much for your answer. Do anyone have question? Oh.
Thank you for your very interesting talk. And I saw it seems like now the AI machine now is kind of task-dependent AI, RNN. So do you have any general picture or the architecture for a general purpose AI? For example, concept level, or to fetch the memory, just like a computer have a memory and computational units like that. Do you have any general picture of this to the AI complete goal?
Yeah, we were trying to like come with this in that paper, Roadmap to Machine Intelligence, because we don't really know how to build this machine. We can just like name some of the properties that we think the machine should have. So we kind of like see this blurry image of that goal that we are trying to describe, but we are still far away from like being able to exactly specify how the machine would look like. So this is like discussed in the paper, and I was trying to like go a little bit quickly over like the properties that we think the machine should have, and yeah, it's a very difficult question. So yeah.
Thank you.
So probably we have time for the last question. If anyone have the question. So if not, let's thank our Dr. Mikolov again. Before the end of this session, we have a small souvenir for Dr. Mikolov. Or coffee break, and the coffee break is at the second floor, so you can see a very clear instruction outside.